Hello again. We are going to discuss the analysis of variance topic. We continue from the previous session to discuss the analysis of variance. In the last session, we started with discussing the problem and the experimental design for which we need to use the analysis of variance or ANOVA test. And we mentioned that the analysis of variance is needed to test the hypothesis that the three or more population means are equal. So the null hypothesis is usually like that. Mu1 equals mu2 equals mu3 and so on. If we have three population means and we want to test the equality of these three means, then H naught will be mu1 equals mu2 equals mu3. The alternative hypothesis is always like that. HA is none or not all the means or population means are equal. Not all of them are equal. Maybe one of them is different from the rest, and the rest are equal. Or two of them are different from the rest, or all the three of them are equal, and so on. So at least one of these population means is not equal to the rest. So none of the or not all the means are equal. To test this hypothesis, this null hypothesis, the equality of the three or more means we need to use the analysis of variance table. And we discussed in the last session how to build this ANOVA table. And we put usually the source of variation, then the degrees of freedom, then the sum of squares in different columns. Then we calculate the mean squares and the F ratio. And it is the most important thing in that table is the F ratio, which is the test statistic. So F stat is usually the division of mean square among groups divided by the mean squares within a group. So the mean squares among groups is the sum of squares among groups divided by its degrees of freedom. And the mean squares within groups is the sum of squares of within groups divided by its degrees of freedom. So this ratio is the test statistic actually, which has the F distribution. That's why we call it F stat. F distribution is probability distribution, like the normal distribution and the t distribution and chi-square distribution. So it is one of the distribution and it has tables. This distribution has two values for the degree of freedom, the numerator and the numerator. So the two degrees of two values for the degrees of freedom, right? So the two values are c minus 1 and n minus c. The c is the number of groups, and n the number of observations in all samples. So the first degree of freedom usually is the c minus 1, and the second one is n minus c. And that is the test statistic. We calculate it, we compute it, and then we compare it with the tabulated F distribution. That is what we get from the table. So we get that from the table. So like that. So in this table, as we said, we have two values for degrees of freedom, c minus 1 and n minus 1. we look at the significance level, the required significance level, which is alpha. Usually, all the significance level, all alpha, is on the right-hand side. It is one-sided test actually. This is usually is one-sided test because the F ratio itself, the F statistic itself is always positive. Now, it doesn't take negative values. So the alpha level, the alpha is always on the right hand side, all alpha. We do not divide it by 2. So we get it in this area, and this is 1 minus alpha. And we go to the table with the value of alpha and the 2 degrees of freedom. We look at its usually the F statistic or F distribution has that many pages for the table. We find the suitable table which has the 2 degrees of freedom, the two values of degrees of freedom, and we look at that value of significance level alpha and find this value, and it will be the critical value here. And we compare it with the calculated or computed F statistics. If it comes in the this region, which is the rejection region, we reject the null hypothesis. So the mean or population means are not equal. But if it is within this region, if it is small, then that's not rejection region. So we cannot reject the null hypothesis, and in that case, we do not have enough evidence to reject the null hypothesis. So we use the hypothesis that they are not equal. So the decision rule reject each note if stat which is computed the value is greater than the F alpha, which is the tabulated value, the theoretical value of F. The theoretical value of F alpha is the theoretical value. It is this we get from the table. So otherwise, do not reject, or do not have enough evidence to reject this hypothesis. Now, let us see an example. In this example, we want to see if 3 different golf clubs yield different distances. We randomly select 5 measurements from trials in an automated driving machine for each club. So we have 5 observations in each club, 5 observations, right? And at the 5% significance level, is there a difference in mean distance? Is there a difference in the mean difference? Again, we have 3 clubs and we have 5 observations in each club. And when we want to test whether there is a difference between the population means for these 3 clubs, right? This is the problem. And so we test the null hypothesis mu1 equals mu2 equals mu3. That's the values, themselves, the observations actually. So we have 3 clubs and we have the overall mean. That's the overall mean, and we found the first group mean and second group mean and third group mean. They would look different like that. So we calculate first the means. The first group mean x1 bar equals 249.2. Right. The second group mean equals 226. which is x2 bar, and the third group mean, which is x3 bar, equals 205.8. These are the three group means. Now, the overall or the grand mean, which is x bar, equals 227, right? 227. So we want to test whether mu1 equals mu2 equals mu3, or at least one of these three means is different, right? Again, these are the observations. And we computed the x1 bar, the first group mean, the second group mean, and third group mean. And we have number of observations in each group, in 1, and 2, and 3, and all equals 5 here. And that's the overall or grand sample mean. And the number of all observations N is 15, and the number of group C is 3. So we calculate the two sum of squares as usual. Either we can calculate the first, this one SSA, and SST, the total sum of squares, because this value plus this SSA and SSW equals SST, the total sum of squares, right? So any two of them will be enough, because if we have these two, then we sum up these values, we get the third. Or if we have the total sum of squares and this one, which is easier to calculate, and then we subtract this value from the total sum of squares, we get that one. Right? So we need to calculate only the two, and the rest will come up alone. No problem with that. It's easy. So because this and this equals the total of sum of squares, so you need two only of them. So the first one is like that. We have the overall mean, which is 227. We subtract it from each observation and square this difference and multiply each difference squared by the number of observations in its groups. Actually, in its group might be here in this case we have the number of observation in each group is the same, but not always we have the same thing. It can be different. Here 5, it can be different. Here this is different from this value, because it can be the number of group in each the number of observation in each group can be different. Not always they are the same. We have here in this special case we have 5 observations in each group, but sometimes it can be 5 in the first group, 10 in the second, 15 in the third. It depends, right? So we calculate the SSA like that. As we mentioned, the difference between each observation and the overall mean, and multiply the square difference by the number of observation in that group, and sum up all these differences. It will come like that. SSW, if we do not calculate the total sum of squares, SSW will be like that. We sum up the squared values of the difference between each observation and the average of each group, and divide them, and the sum up them will be 1119.6. 1119.6, right? So if we have these two sums of squares, we need to get two mean squares. The MSA, the mean square of among group, and MSW, mean square, within a group. So the first one, mean square among group, is the SA divided by its degrees of freedom, 3 minus 1, C minus 1. And this W is the MSW is the SSW divided by N minus 1, which is the SSW divided by 15 minus 3. Not N minus 1, but N minus C. N minus C. The result will be 93.3. Now we need to calculate the F statistic, which is the division. We divide the MSA over MSW. This value over this value. So this value over this value, we get this value. That's the F statistic. So this is the computed F ratio. The computed F ratio. We want to compare this with the tabulated F ratio, like that. Now, we have first the null hypothesis is mu1 equals mu2 equals mu3, which means all population means are equal. The alternative hypothesis is not all mj are equal. At least one of the mu's or one of population means is different. At least one different from the rest. Maybe two or three or whatever. At least one of them is different. That is the alternative hypothesis. So in order to find the tabulated F statistic, we need the alpha level, which is here 5%. If it is not given for us, then it will be 5% alpha level. And it will the F statistic is always one-sided test, so that will be on the right-hand side. So all alpha level like this on this side. And the F statistic have two values for the degrees of freedom, df1, df2. df1, we calculated is C minus 1, the number of groups minus 1, 3 minus 1, which is 2. The df2, the other the degree of freedom, is n minus C, which means 15 minus 3, which is 12. So we look at the table, the F tables, and we find that on the alpha equals 5%, and first degree of freedom equals 2, and second degrees of freedom equals 12, we find this value, which is the critical value. Value of alpha, so that's the tabulated value, which is 3.89, right? So, and this is the rejection region, and the other is non-rejection region. So we want to compare the F statistic, the computed F, this with the critical value. If it is bigger, then it will come in this area, which is the rejection area. And that's the case here. It is bigger, much bigger than the tabulated F. So in this case, the F statistics comes within the rejection region. So the decision will be reject H naught at alpha or significance level equals 5, because this is very big and makes the computed F statistic in the rejection region. So we must reject H naught at alpha equals 5%. So the conclusion is that there is an evidence that at least one mu differs from the rest. So not all population means are equal. Okay. So if we use Excel sheet, if we use Excel sheet, we will get the same result. We use the function of the Excel. I will show you what the function is, and we find this. We put these values, and the function produce this table, the ANOVA table, and we get the F critical, which is the computed if. Not this is the tabulated one. It will, the Excel will give you the tabulated. You know, if you use the if you use the Excel sheet, you do not need to look at the table. So the Excel will give you the critical value and the computed value, and also the p-value, which you will never be able to compute it by hand or manually. Only in computers you can calculate the p-value for the F statistic. So this is the F statistic, the same as what we got by hand, the F statistic, and this is the p-value, which is very small, and this is the critical F, which is the tabulated F, and this is this value is much bigger than this. So the decision will be to reject the null hypothesis, which is the same decision which we get. And also using the p-value, as long as this value means 4.99 multiplied by 10 to the power of minus 5. To the power of minus 5. That means you need to move the decimal point 5 spaces. So it will be 4, the decimal point here, you move it 5 spaces. So 4, 0, 0, 0, 0, then decimal point. So this value is read as 0.0000499. Right? 4 zeros, then 499. That's the value, which is very small, very small. According to that, also, we must reject the null hypothesis, and the decision will be at least one the population mean is different, right? Another example now. In this example, a production manager wants to see if three assembly methods have different mean assembly times in minutes. So the measurements in minutes, time in minutes. That's the dependent value. 5 employees were selected at random and assigned to use each assembly method. So every method assigned with 5 employees. So 5 observations for each method. And the problem is that at the 5% level of significance, there a difference in mean assembly times. So we want to test whether the population means of assembly times are significantly different or not. So these are the observations, method 1, method 3, method 2, method 3, and we have in each method 5 observations, right? This is the observation, and as usual, we calculate x1 bar, x2 bar, x3 bar, and n1, n2, n3, 5, 5, 5. It's not always 5, but it is by chance that comes into example n equals 5, and n here equals 15, and c equals 3, but not all cases. But just because we have 3 groups, and in each group we have 5, 5, 5. That's all. So we have calculated the group means and the overall mean, right? And so you need to calculate the SSA and SW as the previous example. That's in Excel sheet. We got them like that. And then from that, we divide the SSA by n C minus 1. which is 3 minus 1, we get that, and MSW, we get it by SW divided by N minus C, which is 15 minus 3, we will get that. So if the statistic is this value over this value, we get this value. So it is MSA over MSW. We get this value 3.8853. That's the F statistic. And we need to get the F critical, tabulated F, and compare it with the computed F, right? So the null hypothesis, again, is mu1 equals mu2 equals mu3. And the alternative hypothesis is that not all population means are equal. At least one is different. So the alpha level is 0.25, and the degrees of freedom n minus 1, C minus 1, and n minus C will be 2 and 11. And we calculated the test statistic, which is F statistic. So computed F, and we got it in the last page. It was 2.6311, right? But the critical value from the table, we can get it with alpha equals 0.25 and degrees of freedom 2 and 12. We look at find the page of the statistic according to these values, alpha and 2 and 12. We find it under the value of 3.89. So that's the critical value of F, or tabulated value. And this is the F statistic 2.63, which is less than the tabulated F. If it is less, then it is not in the direction region, so you cannot reject the null hypothesis. That's the decision. We cannot reject H naught at alpha level, which is 5%, 0.25. So there is not evidence that at least one MUJ differ from the rest. No evidence to reject the null hypothesis, right? Again, how to do that in Excel? You go to data, then at the right hand corner, the top right hand corner, you find data analysis, press it, and find in the pop-up menu ANOVA single factor, and mark the observations. You will get this result. If you mark correctly the observations of 3 groups, you will get all these results. And then you will find the F ratio, which is the same F ratio we get, computed F ratio, and the critical F, the tabulated F, you get it like that. This is the result from Excel directly, which is exactly the same as we got from the calculation. But here also you get the p-value, which we cannot calculate it actually by hand, only using Excel or statistical package. It cannot be calculated by hand in this case. It's very difficult or impossible to calculate it by hand. But we get that, which is very big, much bigger than 5%, or bigger than 0.05. So as long as it's big, then the result is that we cannot reject the null hypothesis. We reject it only if the p-value is very small, as usual, but this is not very small p-value, so we cannot reject the null hypothesis at this level. So we can say that the three population means may be equal, right? That's it for this session, and that's we finished describing the one-way ANOVA, and I hope everything is clear. Thank you very much, and see you in other subjects. Bye bye.